Okay, let's continue talking about the techniques of differentiation. And this particular section, we're going to talk about using the product and the quotient rules, and then to find a derivative, and then use the higher order differentiation techniques. So objectives, we will find the derivative of a function using the product rule, find the derivative of a function using the quotient rule, find the derivative of a trigonometric function, find a higher order derivative of function. First of all, let's take a look at the product rule. Right? So the product rule, if you put in a very simple, we have two functions, f and g. So the derivative of that will be f prime times g plus f times g prime. Okay, we put in a very simple expression. That would be the easiest thing to do. Okay. So the product rule, the product of two differentiable functions, f and g, is itself differentiable. Moreover, the derivative of f times g is the first function times the derivative of the second, plus the second function times the derivative of the first. So as I mentioned before, right, you can just view that as f represent function f of x, g represent function of g of x. So it's going to be f prime times g plus f times g prime. But if you put in the function notation, it will be f of x, f prime x times gx, and g prime of x times f of x. Okay. Alright, so let's take a look at this example. Using the product rule, find the derivative of h of x equals to 3x times minus 2x squared parentheses times parentheses 5 plus 4x. Okay, so we assume this is f. That's going to be g. Since f equals to 3x minus 2x squared, f prime, using the power rule, will give us 3 minus 2 times 2 times x 2 minus 1. So this becomes 3 times minus 4x. Okay, that's f prime. So g equals to 5 plus 4x. So g prime, derivative of 5 is 0. Derivative of x is 1, so 4 times 1. So we end up with 4. Now we can just apply the derivative of h of x, right? Which is same thing as derivative of f times g. So it's f prime times g plus f times g prime. So now just replace f prime, g prime with the given numbers. Okay, so it's going to be f prime is 3 minus 4x times g is 5 plus 4x plus f is 3x minus 2x squared, and g prime is just 4. Okay, then we just got to distribute it and combine like terms. 3 times 5 gives us 15. 3 times 4x gives us 12x. Negative 4x times 5 gives us negative 20x. Negative 4x times 4x is negative 16x squared. The very last one, 3x times 4 gives us 12x. Negative 2x squared times 4, negative 8x squared. Okay. Then we start combining like terms. So 15 remains. 12x minus 20x gives us minus 8x plus 12x minus 16x squared minus 8x squared. So this becomes 15 plus 4x. 12 minus 8 is 4. 4x minus 24x squared. Okay, if you rewrite it in the increasing order, in decreasing order in terms of x, that will be negative 24x squared plus 4x plus 15. Okay, so that's going to be the final answer. And next thing, let's take a look at a quotient rule. So the quotient rule, put in a very simple expression, be two functions, one on the top, one on the bottom. So that'll be a prime of g times g minus f times g prime over g squared. Okay, that'll be the simplest thing to do. Let's take a look at the theorem, the quotient rule, the quotient f over g of two differentiable functions. F and g is itself differentiable at all values of x for which g of x is not equal to 0. Moreover, if the derivative of f over g is given by the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. So in this case, just like what I did before, right? F over g. So it's going to be f prime times g minus f times g prime over g squared. Okay. So let's use this to solve one of the problems using the quotient rule. As you can see, the power rule is everywhere, so make sure you can apply the power rule properly, because it's very, very important. Okay, so here we assume this is f, that's going to be g, right? So once you figure out what is f, what is g, what is f prime, what is g prime, you're ready to go. So 5x minus 2, so f prime, derivative of f, derivative of 5x becomes 5, derivative of negative 2 becomes 0, right? Okay, so it's 5. G equals to x squared plus 1, g prime, derivative of x squared becomes 2x, derivative of plus 1 becomes 0. Okay, so 2x. Okay, figure out that. Now we can apply the quotient rule. So derivative dy over dx equals to d over dx f over g, right? Is a quotient. So we have f prime times g minus f times g prime divided by g squared. Now just replace f g f prime g prime with the given expression. Yeah. Okay. So f prime is 5 times g is x squared plus 1, put in parentheses, minus, remember, notice that this is minus, so not a plus, it's different from the product rule. And minus f, which is 5x minus 2 times g prime is 2x over g squared, right? So it's going to be x squared plus 1 squared. Okay, so let's expand the numerator and then simplify that. Okay, so we get a 5 times x squared gives 5x squared, 5 times 1 gives us 5. So now we have negative 2x, put 2x in front, 5x minus 2 over x squared plus 1 parentheses squared. So let's expand it. So we have 5x squared plus 5, negative 2x times 5x is negative 10x squared, negative 2x times negative 2, give us positive 4x. Then almost there. Then combine like terms. 5x squared minus 10x squared is minus 5x squared, and plus 4x plus 5. So that's numerator, and denominator is x squared plus 1 squared. So that's your final answer. So make sure apply the rule properly, and you end up with the correct answer. So let's also take a look at the derivatives of trigonometric functions. Okay, knowing that derivative of sine cosine, you can use the quotient rule to find the derivative of the 4 remaining trigonometric functions, right? By using sine cosine. So as you see, right, derivative of sine x is cosine x, and derivative of cosine x is negative sine x. Okay, so derivative of tangent x, I'm gonna prove one of them, right? Let's see, derivative of tangent x, we can write tangent x as sine x over cosine x. Now f is sine x, g is cosine x, so f is sine x. So f prime, derivative of sine x is cosine x, and g is cosine x. Derivative of cosine x is negative sine x. Now let's apply the quotient rule. F prime cosine x times g cosine x minus f sine x times g prime negative sine x over cosine x squared. So on numerator we get cosine x squared plus sine x squared over cosine x squared. Okay, cosine x squared plus sine x squared give us 1 over cosine x squared. Okay, you can split as 1 over cosine x times 1 over cosine x. That becomes secant x squared. Okay, so this is a quick proof why this is true, given that we know. You can also use the limit definition of derivative to do this, to prove this, but this is probably easier. Derivative of tangent x becomes secant x, right? Derivative of cotangent x becomes negative cosecant x squared. Derivative of secant x becomes secant x times tangent x. Derivative of cosecant x becomes negative cosecant x times cotangent x. Okay. So once you know all of this, we can move on to the next slide. So let's see. Okay. So A, we got a y equals x minus tangent x. So derivative of x becomes 1. Derivative of tangent x becomes secant x squared. Okay, so the derivative dy over dx equals 1 minus secant x squared. Now actually, we can simplify this a little bit if you want to do that. Factor out negative sign becomes that. So secant x squared minus 1 becomes tangent x squared. Right, if you want to simplify into single trigonometric identity, you can do that. And B, we get y equals to x times secant x. Here, this is our f, that's our g, right? So f equals to x, so f prime derivative of x becomes 1. And g equals secant x. So g prime equals secant x times tangent x. Now we use a product rule. So then this is dO dx. This is f times g. So this is basically f prime g plus f times g prime. F prime is 1 times g secant x plus f with x times g prime, which is secant x times tangent x. Okay. So now here we both have secant x. You can factor out that. In first term only 1 remains. Second term we have x times tangent x remains. We're going to simplify that. That's exactly as what I have here. Okay, so that's how you apply the product rule to solve this problem. And just make sure, you know, anytime when you encounter all this kind of complicated, after find a derivative, you may encounter kind of complicated, you know, expression. Just have to simplify that a little bit, right? Just like the example go over that, after simplifying it becomes a much simpler expression. Just make sure you do that. Simplify as much as possible. Simplify as much as possible after taking a derivative. Okay, so next thing, let's take a look at the higher order derivatives. First of all, we're gonna visit one of the 4 major problems in derivatives. Remember, the velocity function is achieved by differentiating the position function, and you can obtain an acceleration function by differentiating a velocity function. So another way of taking a look at this, you can obtain an acceleration function by differentiating a position function twice. So this is position function. After taking the first derivative, you end up with a velocity function. Then after taking the position function twice, taking the second derivative of position function, then you end up with the acceleration function. Okay. So velocity function is the first derivative of position function, and acceleration function is the second derivative of position function. The function given by a parenthesis t is the second derivative of s of t, is denoted by s double prime of t. The second derivative is an example of higher order derivative. You can define derivative of any positive integer order. For instance, the third derivative is the derivative of the second derivative. So this is like a sequence, right? First of all, you get a y prime, first derivative, y double prime, second derivative, y triple prime, third derivative, y to the fourth derivative, y to the nth derivative. Okay, this is just one way to write it. Another way would be this: f prime of x, first derivative, f double prime of x, second derivative, f triple prime of x, third derivative, f fourth prime of x, fourth derivative, f n prime of x, which is nth derivative. And that's the second way of writing that. Third way, dy over dx, first derivative, d squared y over dx squared, second derivative, d third of y over dx cubed, okay, third derivative, d for y over dx to the fourth derivative, and dmy over dx to the nth derivative. Okay, And this is okay. We have several different ways of writing this. This is another way of writing that. D over dx f of x, d squared over dx squared f of x, d cubed over dx cubed f of x is first derivative, second derivative, third, fourth, and nth, right? And the last way of writing that, capital N represent derivative x, y. This is actually 1 here, but they omit it. So first derivative, second derivative, 2, third derivative, 3, fourth derivative, and derivative. Just make sure you know you will be able to distinguish all these different symbols for derivatives, for higher order derivatives. So let's take a look at example. Find the acceleration due to gravity. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer falls at the same rate on the moon. The position function for each of these falling objects is given by s of t position function equals negative 0.81 times t squared plus 2, where s of t is the height in meters and t is the time in seconds. And what is the ratio of the Earth's gravitational force to the moon? So gravitational force, that's AT, acceleration function. So we need to find out the acceleration function. So the acceleration function is the second derivative of the position function. So first of all, s of t equals that s prime of t, using the power rule, negative 0.1 times 2 times t plus 0, right? So we end up with negative 1.62 t times t. Okay, so then s double prime of t will be negative 1.62, and this is meter per square second. Okay, so that's our gravitational force on the moon, which is acceleration function. So this is just a way to look at it. Acceleration due to gravity on the moon is negative 1.62 meters per second, which is meters per second square. Now, because the acceleration due to gravity on Earth is negative 9.8 meters per second squared, the ratio of the Earth's gravitational force to the moon is negative 9.8 over negative 1.62. If you divide it, it's approximately 6 times. Okay,